late stages of volcanic eruptions. They don't contain water, but they were sort of short-lived volcanic features, and some of these cinder cones are being quickly destroyed by mining, which gives us a nice view of their interior, and paleontologically they're interesting. What you also will notice is that almost any natural stone that you see here, especially in the old houses, is this red or yellowish color. All of this is then the lower Triassic Buntsandstein that has yielded the fossils that we will be seeing soon.
There are stones, but it is expensive. The people prefer other material, and it is a configuration of iron. This difference of color. It goes.
And you said he covered it with sand?
Yes.
That's a good idea.
But it's entirely with sand. Yes. But it is a lot of work, because you must first bring them from the quarry.
Right.
All the top is full of stones, shales which are not prepared. Here is the counterpart of the specimen here. I don't know where. Probably this one.
Right.
So it is exactly. It has a conifer structure.
So
ovulate.
These are the male ones?
No, there are no male. They are macerated. It is difficult to say.
Does this kind of adaptation show up? And the answer is not in Holzmaden. It shows up in the early late Triassic of China with different groups. There are black shales in China where you see the same thing. And one idea is that, of course, to have this you need some evolutionary time, but you definitely need tree trunks. Now what if there were no trees in the early Triassic? Because after the PT extinction, that's one idea that Carl had mentioned already, that possibly there were no trees. So
that's not my idea. I'm just saying about period.
Well,
the vegetation was mostly not trees.
But it's interesting to note, of course, to have this kind of adaptation, you have to have tree trunks in the water.
Well, almost regularly falling in.
Right, regularly falling. And the other thing you have to have is that nobody destroys these tree trunks. And apparently that stopped happening, this kind of niche close, when the shipworms evolved. Bivalves that started eating up wood very rapidly.
Fossils of different fascias. And these fascias you can see here from the coral reef to the peripheral reef, and going a little bit deeper here. Certainly this is condensed. This is not one-to-one. The distance here should be much wider. But anyway, all the organisms here are again in natural size. These big crocodiles, the biggest ones we know, just to try to get them as prey. The smaller ones.
The question why it was anoxic is more difficult to answer. Somehow the basin was restricted, so water at least for part of the year, there was no exchange of bottom waters with the Tethys Ocean. We still have a similar setting as we had in the Muschelkalk. The basin was restricted, but not to the same extent. These layers, this is what they're digging up, and then you can see the big slabs here. Those are used for construction, and to get them out, then they have to remove the overburden and dump them. And these accumulate in the ichthyosaur stomach. So it is assumed that ichthyosaurs really fed on various kinds of cephalopods most of the time. Not on the ammonites, because they were protected by the shell. Who is the director of the Solnhofen Fossil Museum that is run by the community, and stones, as you can see, are laminated carbonates. As we saw, the going up section here, the Jurassic, gets more and more carbonate rich, and to have carbonate production you have to have two factors. Can be no clastic input, because any clastic input of mud or sand or whatever will inhibit carbonate production. And the other thing is you should have warm waters. So partially, of course, it was warmer in the Jurassic, but partially we were at a different latitude than we are now. The question is really, where does the lamination come from? It's always the same question, that if we have these exceptional fossil deposits, we get them because we have laminated sediments that are not disturbed by any bottom life. It's too light colored, and I haven't tried it, but I don't remember, if you knock at it and you smell, there's no high, or the organic content is minimal. So we have to have another factor that actually inhibited bottom life, and in this case the lamination is due to water chemistry. In this case, to high salinity. Here fossils really are extremely rare, which is sort of surprising if you hear about a world-class, or possibly the most important fossil deposit there is in the world, because Archaeopteryx, that came from here, is the most important fossil from an evolutionary biological perspective. And we have to ask, what are the geographic or paleogeographic parameters that produce this hypersalinity? And in this carbonate platform there were shallow basins that became, at times at least, completely hypersaline and devoid of life, and they were too small to have any significant currents in them that would have mixed the water column, and then you get this laminated facies.
And they're not finding this wood, so they're hypothesizing that it's shrubby vegetation. And that's basically what's known so far.
Next to nothing.
Next to nothing, so good little niche to move into.
Volcanoes of Oligocene age, and that have been exhumed. There's the famous Seven Hills. This is important in German history, because this is where Siegfried of Wagner fame actually slayed the